Hello my dear 2PO2 students, welcome to Deeksha Karnataka YouTube channel, and today I am going to discuss one of the important chapter for your PU2, which is semiconductors. If you study this chapter, you are going to get a lot of questions coming in your final board exam, not only in pre-board but also in final board exam. So don't go anywhere, watch till the end so that you will be confident in the exam, so that you will say that okay, I am confident I will be scoring marks from this chapter. So let's start. First of all, let us look into the blueprint of this chapter. So in the blueprint you can see that there will be 1 marker question 1, there will be short 2 marker question 1, and there will be no 3 marker question coming from this chapter. So 3 marker portion is blanked, and 1 guaranteed 5 marker question will come from this chapter. Total marks allotted for this chapter is 8. Now in the MCQ section, what we are going to discuss in today's session, we are going to discuss 15 MCQs. We will also be discussing 2 marker question 5 and 5 marker questions 3, that is sufficient to score the marks 8 marks that is allotted in this chapter. So let us start. First, we will, as usual, we will start with MCQs. MCQs are the part where you struggle the most, so don't skip the video, watch till the end so that you are confident with all different types of MCQs. In the figure, EV and EC are the valence band and conduction band corresponding to an extrinsic semiconductor. Capital E is the energy state corresponding to the impurity present in it. The input, the impurity present it can be. So here if you see that the level of impurity shown over here are like this. So this is a donor level. This is called acceptor level. This accepts electron from the valence band. It accepts electron in the valence band and creates more number of holes in the valence band. That is, it is a p-type semiconductor. So this is a p-type semiconductor. Now p-type semiconductor requires what is the valency that we need to dope into an intrinsic semiconductor to make it a p-type? We need a 3 valence. Valency should be 3. Okay, 3-valent or trivalent substance. Now if you see all the options, arsenic is a pentavalent substance, phosphorus is also pentavalent, antimony is also pentavalent, only indium is a trivalent element. Okay, so we will dope it with the trivalent element, that is indium. Okay, now let's move on to the next question. The column 1 is the list of materials and column 2 the list of energy band gaps E. Identify the correct match. Conductors Eg less than 3 electron volt, insulator Eg equals to 0 volt, semiconductor Eg greater than 3 electron volt. Now we know the match over here that conductors have 0 band gap, that means Eg equals to 0. Insulators have very high band gap, so their band gap should be greater than 3 electron volt, and semiconductors have band gap between 0 to 3 eV, so it will be less than 3 eV. So let's see the matching. So 1 is matching with B, 2 is matching with C, and 3 is matching with A. So if you see that 3 is matching with A is given only once, we will match the first one also. So this is the correct matching. Obviously option D is correct. Clear? Next question. When a forward bias is applied to a PN junction, it raises the potential barrier, reduces the majority current to 0, lowers the potential barrier, raises the width of the depletion region. So forward bias means what? When you apply forward bias to a diode, what happens is its depletion region, which was wider, slowly starts to become 0. It will start to go towards 0 and slowly disappear when the forward voltage is sufficient enough. Okay, so it is basically reduces the potential barrier or lowers the potential barrier, not the majority carrier. It does not change majority or minority carriers. Okay, it only lowers the potential barrier. Potential barriers lowers and it becomes 0 as you keep on increasing the forward bias voltage. Energy band gap in conductors, insulators and semiconductors are respectively E1, E2 and E3. The relationship between them is, so for conductor E1 is equals to 0. For insulators E2 it is greater than 3 electron volt, whereas for semiconductors E3 it is less than 3 electron volt. Okay, so what we can say is that E1 is the smallest, E3 is in the middle, E2 is more than all the other options. So as you can see, correct answer is E1 is smallest, E3 is next, and E2 is the largest. So correct answer is option D. Clear? So 4, option D is correct answer. Next, P-type semiconductor is electrically positive, negative, neutral. As temperature increases, it becomes negative. So no matter whether it is a P-type, whether it is a N-type, whether it is a intrinsic, whether it is extrinsic, it is always electrically neutral. Does not matter what. Semiconductors normally are always electrically neutral. So P-type, N-type does not matter, because total number of positive charge, total number of negative charges are always equal. So it is electrically neutral. Next question, in intrinsic semiconductor at room temperature, the number of electrons and holes are equal, 0, unequal, infinite. So in intrinsic semiconductor, what is intrinsic semiconductor? Intrinsic semiconductor are those which are pure semiconductors. So normally the total number of electrons are equal to total number of holes, and again it is electrically neutral. So it is equal. In intrinsic, it is equal. Unequality comes from the doping, and if it is not doped, it will always be equal. When a PN junction diode is in forward bias, which type of charge carriers flow in the connecting wire? Ions, protons, holes, free electrons. So when a PN junction diode is forward biased, always in the carrier wire, connecting wires, free electrons flows in the in case of whether it is a PN junction, whether it is a P type, whether it is N type. Okay, it will always be free electron in the connecting wires. Connecting wires will always have free electrons. Inside the diode there may be holes or maybe electrons, but outside in the connecting wires only free electrons will pass, because it is mentioned in the connecting wire. Wire always have free electrons, and that's how they conduct the current. Holes cannot escape the diode and come to the connecting wire. So only free electrons is the correct answer. This is a very tricky question, by the way. Be very, very careful. Next, a positive hole in a semiconductor is absence of free electrons, an artificially created particle, an antiparticle of electron, a vacancy created when an electron leaves a covalent bond. So a positive hole is a vacancy created when an electron leaves a covalent bond. Okay, it is not absence of free electrons. Remember, absence of free electrons is there in the insulators, but hole is not something which is due to absence of free electrons. It is when an electron is moved out of a covalent bond, the vacancy that is left behind, that vacancy actually behaves as a covalent bond. As a hole. Next, the energy gap in case of which of the following is less than 3 electron volt, greater than 0, less than 3 electron volt? It is basically germanium. Germanium is a quantity which is a semiconductor. So semiconductors have energy gap less than 3 electron volt. Aluminium, iron and copper, they are all conductors. So for them the band gap is equals to 0, not less than 3 electron volt. Okay, less than 3 electron volt criteria is only applicable to germanium. Even though aluminium, iron, copper are 0, you cannot say they are always less than 3 electron volt. Germanium on the other hand is always less than 3 electron volt. 0, so it should be mentioned that but not 0. It should have been mentioned that here, but not 0. Okay, not equals to 0. Next question, in the depletion region of an unbiased PN junction, the majority charge carriers are only electrons, only holes, both electrons and holes, neither electrons nor holes. So in the depletion region, it is completely depleted of all the charges, all the possible charge carriers. So neither electrons nor holes are correct answers. In unbiased PN junction, in the depletion region, no charge carriers present. That means neither electrons nor holes. Okay, nobody is there, everyone is dead. So that's why it is called a depletion region, depleted of all the free charge carriers. Now question number 11, the donor energy level ED is slightly below the bottom EC of the conduction band. In case of, so donor energy level, that means the band diagram, if you draw, you will observe like this. This is valence band, this is conduction band, and donor level is here, which donates electron to the conduction band, so that conduction band has more number of free electrons. Donor level appears only in case of n-type of semiconductor. N-type semiconductors have donor level, p-type semiconductors have acceptor level to create more number of holes. Okay, so remember this small trick, that n-type has donor level. Donor means it donates electron, donates means it will have more number of extra free electron. Acceptor means it accepts electron, that means more number of holes are created. Okay, that is the meaning of donor level and acceptor level. This is because of the impurity. This comes into the picture due to the impurity that is present inside the semiconductor, right? In an n-type silicon, which of the following statement is true? Electrons are majority carriers and trivalent atoms are dopants. So n-type semiconductor means, what is the n-type? N-type's majority carriers are electrons, and what is the dopant? Dopant is a pentavalent material. Okay, pentavalent, for example, phosphorus, arsenic, antimony, they are pentavalent. So in case of n-type silicon, even though first part is correct, electrons are majority, trivalent is not correct, so this is not correct statement. Electrons are minority carriers, so definitely electrons are not minority, so this is incorrect. Holes are minority carriers and pentavalent atoms are the dopants. So holes are minority for n-type. Obviously, if electrons are majority, then minority has to be there, so holes are minority, and pentavalent is also correct, so both this condition is satisfied, so option C is correct. So be careful, again be careful, don't just see okay electrons are majority and you mark it. You have to read the complete statement to answer this type of questions properly. Next, in an unbiased PN junction, holes diffuse from P region to N region. Okay, so in unbiased junction, holes diffuse from the P region to the N region because free electrons in the N region attract them. They move across the junction by the potential difference. Holes concentration in the P region is more as compared to the N region. All of the above. Here it is actually all of the above. Okay, free electrons in the N region attract them. Okay, holes getting attracted by opposite charge. They move across the junction by the potential difference. There is already a potential difference developed. Okay, electrons started diffusing, so electrons are also started coming towards the hole, so there is a potential difference developed, and that's why electrons started to move. Holes concentration in the P region is more as compared to N region, that is also one of the region. Okay, so all of the above is the correct answer, even though I have some reservation about this. Okay, potential difference is actually developed in the opposite sense, but free electrons N region attract them, so that is one region, so that's why I have answered all of the above. But otherwise, I think all of the above is a incorrect statement. More correct will be hole concentration in P region is more compared to the N region. Okay, this actually not true. The potential difference is actually developed in the opposite direction. Once what should I say? Once the hole starts to move from P region to N region, the potential difference originates in the opposite direction. That gives rise to depletion region. Free electrons do attract them, but the attraction force can be ignored, very small. Okay, and even holes are not actually something which is a real particle, so that in that sense you can ignore this statement as well. So main region is concentration of holes in the P region is more than in N region, so that's why electron starts to shift. Okay, if you are living somewhere where a lot of people are there inside a room, what you want to do, you want to move towards another room which is empty or vacant, right? So that's what holes are doing. Next, when a forward bias is applied to a PN junction, it raises the potential barrier, reduces the majority charge carrier to 0, lowers the potential barrier, none of the above. So when a forward bias is applied to a PN junction, it lowers the potential barrier. It lowers the potential barrier. Which of the following is used to convert AC to DC? P-type semiconductor, N-type semiconductor, diodes, all of the above. Only diodes are used to convert AC to DC. P and N-type individually they cannot convert AC to DC. That means rectification. Rectification process, AC to DC is the rectification process. We will see that. So rectification is possible only by diodes. So PN diodes or normal diodes that are used to convert AC to DC. So all the MCQs are over. Now let's buckle up for the longer version of the question. Name the majority and minority charge carriers in N-type semiconductors. Okay, so what is the majority charge carrier? What is the type? N-type, so majority must be electrons. N-type comes from negative type, P-type comes from positive type. Okay, so remember that. So majority is electron, negative type means electron has to be majority, and minority are those who are present in small quantities, small numbers, so that is holes. Okay, next, what are intrinsic and extrinsic semiconductors? So intrinsic semiconductor are those pure semiconductors are called intrinsic semiconductors. The presence of charge carriers, electrons and holes in an intrinsic semiconductor are intrinsic property of the material, and these are obtained as a result of thermal excitation. Okay, so intrinsic semiconductors are basically pure semiconductors, and charge carriers are intrinsic property of the material, and its conductivity increases with temperature. Okay, the number of charge carriers can be changed by doping of a suitable impurity in pure semiconductors. Such semiconductors are known as extrinsic semiconductors. These are of two types, N-type and P-type. Clear? Easy question. How can a semiconductor diode be forward biased? What happens to the width of the depletion region when forward bias voltage is increased? So a semiconductor diode is forward biased when you connect the positive terminal of a power source like a battery to the P side of the diode and negative terminal to the N side of the battery. This setup helps to overcome the potential barrier created in the depletion region and allows the current to flow through the diode. Okay, as you increase the forward voltage, the depletion region becomes narrower and slowly disappear. Very important, as you increase the forward potential, depletion region depletes and it goes to zero. Differentiate conductors from insulators on the basis of band theory of solids. Very important. So differentiation means obviously you have to write the difference table. Band structure, overlapping partially filled bands. Okay, in case of conductors, both valence band and conduction band, they overlap. Now large separation between the bands in case of insulators. You can write the same question might come in case of semiconductors also, so you have to prepare that as well. Okay, so they separation is small but still distinct. Energy gap 0 or very small, very large, greater than 3 to 5 electron volt. Okay, 3 to 5 electron volt, better to write 3 electron volt. Charge carriers, abundant free electrons in the conduction band, very few or no free electrons in case of insulators. Conductivity is very high and its conductivity is very low. Distinguish between P-type and N-type semiconductors. So property, doping element, trivalent. Okay, in case of P-type, that is boron, gallium, indium. N-type semiconductor, for N-type semiconductor, pentavalent, for example phosphorus, arsenic, antimony, etc. Majority carriers for P-type are holes, for N-type they are electrons. Minority carriers are electrons, and for N-type they are holes. Charge movement due to holes, charge movement due to free electron. Clear? Now these two questions, 5 marker questions, are very, very important. Full wave and half wave. Out of that, full wave is most important, okay, because it has came more number of times than half wave, but half wave has also came 1 or 2 times, so don't ignore half wave as well. So what type of questions we can expect from this part? So what is a rectifier? Explain the working of a full wave rectifier using a circuit diagram. Draw its input output waveform. Now what is a rectifier? This is a common portion, and after that they will ask half wave or full wave. Now in your pre-board both can come. In your final exam only most important is full wave, but half wave may also come. So prepare, please prepare both of them. The diagrams are also slightly different. So remember, when you start the diagram, on our left hand side there is a transformer present, okay, and you are tapping at the middle center tap. It is called center tap. Okay, from the middle it is the reference point, it is grounded over here. So when this side is positive, what happens is when this side is positive, this becomes negative, and when this side is negative, the other side becomes positive. Okay, so the polarity of the both sides are changing with respect to the center tap, and that's why the diode will be forward bias in one case and reverse bias in the other case. So there are two diodes in full wave rectifier, minimum two diodes should be there. Okay, there are other types of rectifiers where more than two diodes are used, but simplified number of diodes should be two. Okay, now what you have to write? A rectifier is an electronic device that converts alternating current to direct current. One such example, do you know what is the example of rectifier? You are using it every day. Even watching this video, you are using that. So one of the most common rectifier is a charger, mobile charger, laptop charger, or some charger that is being used in your TV. Okay, televisions generally have the rectification happening inside them. Otherwise, for all other devices, laptops, mobiles, the charger itself is the rectifier. It not only rectifies, it is also transform the voltage. So it is actually a combined device. Okay, it changes the voltage as well as it also rectifies from AC to DC. If you read the label on a charger, you will realize that it is mentioned that some 220 volt AC input and some 2.1 ampere 5 volt DC. So that's what the voltage is being reduced, and also the current is also changing, right? Now an AC have two cycles. And AC have two cycles. One is this is called positive, this is called negative. This cycle is called positive, this cycle is called negative cycle. Okay, so during positive half cycle means this cycle. Okay, this is the positive cycle. During the positive half cycle of the AC input voltage, the upper half of the transformer secondary windings becomes positive. So this one becomes positive. Okay, diode D1 becomes forward biased and conducts, allowing the current to flow through the load resistor. So if you see that the P side is positive and the other side is 0, so voltage current will pass from positive to 0. So this diode conducts, whereas the diode D2, this is negative, P side is negative, so that means this does not conduct. So only this diode is conducting. Okay, so allowing the current to flow through the load resistor. Diode D2 is reverse biased and does not conduct because the P side of the diode is negative. So negative voltage means the diode is not conducting. So we are only getting a current through diode D1, and that is also along only one direction. Now if you draw the input output waveform, you will see that this is waveform for A, this is the waveform for B. So when this is the positive cycle for A, for B it will be negative cycle. When it is negative cycle for A, it will be positive for diode B. Okay, so D1 conducts during the first cycle, D2 conducts for the second cycle. Clear? Any doubts? You can ask me later on. During the negative half cycle of the AC input voltage, the lower half of the transformer secondary winding becomes positive, diode D2 becomes forward biased and conducts, while diode D1 is reverse biased and does not conduct. Current again flows through the load resistor in the same direction as during the positive half cycle. So this is the minimum writing, and everything is written perfectly. Okay, so you do not change it or do not reduce this much. Okay, 5 marks you are going to get, so at least have to put some effort, right? So put some extra effort and write exactly as it is showing in here. Okay, next is what is a half wave rectifier. Explain the working of an half wave rectifier using a neat circuit diagram. Also draw the input output waveform corresponding to it. Now if you see the half wave diagram, there is only one diode present, no center tap, so only one diode, one load resistance, and it is a very simple diagram. Okay, diagram is very simple, but do not confuse half wave and full wave. Okay, half wave is slightly different than full wave, so do not confuse with half wave and full wave. Now a half wave rectifier is an electronic circuit that converts alternating current AC into direct current DC by allowing current to flow only during one half cycle of the AC input signal. The other half cycle is blocked, so only half of the AC waveform is used. Okay, now so this is the circuit diagram. So during what happens is that the positive half cycle diode conducts, during the negative half cycle diode does not conduct, so you get a flat line over here. During the positive half cycle of the AC input, the P side of the diode is positive with respect to the N side. The diode becomes forward biased and conducts the current. Current flows through the load resistor RL in one direction and voltage across the load is positive. Negative half cycle of the AC. During the negative half cycle of the AC input, the P side of the diode becomes negative with respect to the N side. The diode is reverse biased and does not conduct. No current flows through the load resistor RL and the output voltage is 0 during this half cycle. Very important. Okay, so the output voltage is 0 for the second half cycle. Now let's move on. Now this is the last question of this chapter. This question you can skip, but I recommend you should also practice this question. No harm done. You are going to get 5 marks anyway, but if you do not have time, you can skip this question. This question might be asked as a 2 marker question, or can become as a 5 marker question along with all the parts. So that's why I recommend to study this question as well. Write 3 differences between intrinsic semiconductor and extrinsic semiconductor. So it can come as write 2 differences between intrinsic and extrinsic, and can be asked as a 2 marker question. So definition: a pure semiconductor with no impurities. Extrinsic semiconductor: semiconductor doped with a small amount of impurity to improve conductivity. Charge carriers: equal number of electrons and holes. Unequal number of charge carriers: majority carriers electron in N type and holes in P type, and minority carriers. Okay, so extrinsic semiconductor has two types of carriers, minority as well as majority, but in intrinsic there is no majority minority, everyone is equal. Conductivity: low conductivity at room temperature, high conductivity due to doping, which increases the charge carriers. Okay, so extrinsic semiconductors, these properties, intrinsic semiconductor, these properties you have to remember. Next, draw the energy band diagrams of N type and P type semiconductors for temperature T greater than 0. Easy diagram, easy to remember, nothing difficult, no rocket science. Here if you see that, first of all, in case of P type and N type, you have to show the corresponding impurity level. Okay, so this is an N type. So in N type semiconductor, this is called donor level. Donor level. Okay, and as you see, this is the valence band, this is valence band, this is conduction band. Okay, so electrons are here in the valence band as well as in the conduction band. More number of electrons are in the conduction band. That means this is an N-type semiconductor. In case of P-type semiconductor, what happens is that this is a P-type semiconductor. Now in P-type semiconductor, this is acceptor level. Okay, this accepts electron. Acceptor level accepts electron from the valence band, so that more number of holes are present in the valence band. Now if there is a objective question which says that in case of P-type semiconductor, holes are located at, so holes are located at valence band, not in conduction band. Remember, this is valence band. Okay, conduction band is almost empty. Some few minority electrons are present. Okay, in majority of the holes are actually present in valence band. Okay, conduction band is consisting of only electrons, whereas holes are present only in valence band. Why so? Because you are breaking a covalent bond, right? Bond happens only because of the electrons taking part in valence band, right? Valence band determines the valency of an atom. So because you are breaking those bonds, that means holes are created only in valence band. Okay, so this is very interesting point for an MCQ objective type of question as well. Okay, so holes are located in the valence band and electrons are located in the conduction band. Okay, so this is the acceptor level P-type semiconductor, and you can show this energy gap 0.1 electron volt, and here it is 0.01 to 0.505 electron volt. Okay, so this is 0.01, this is 0.01 to 0.05. This is optional, but the band diagram should be drawn like this. Holes and electrons should be shown properly. Okay, so this is the end of this lecture. Thank you for watching. I will be back with a new chapter very soon. Till then, bye. So the lecture is over. If you enjoyed this session, don't forget to like this video and subscribe to our channel. And if you have any doubts, any questions, don't forget to ask me in the comment section below. I will try to answer as much as possible. Right? I'll be back with a new lecture. Till then, bye.